Hey, welcome to The Explainer. Today, we're going to pull back the curtain on a hidden mathematical language that, believe it or not, powers everything from your music playlists to your social media feed. It's called set theory, and it's all about bringing a little order to the chaos. So let's dive in.
Think about it for a second. Your favorite playlist is really just a collection of songs. Your shopping list? That's just a collection of things you need to buy. They all seem pretty random, but how do you actually, describe these groups in a way that a computer or a mathematician can understand? Well, it all comes down to a really simple but incredibly powerful idea: the set.
All right, so this is our first, most basic tool in the whole toolkit, a set. Now, the definition looks almost too simple, right? A collection of objects. But the secret sauce is in those two little words, well-defined. That is everything. It means there's no confusion, no debate. You're either in the set or you're out. That's it. So what does well-defined actually look like in practice? Well, if I say the collection of tall students, we've got a problem. What's tall anyway? My idea of tall might be totally different from yours. It's vague. But what if I say the collection of students between 135 and 160 centimeters tall? Now we're talking. We have a clear rule. You're either in that height range or you're not. And just like that, a fuzzy group becomes a proper mathematical set.
Okay, great. We've got the what. We know a set has to be a well-defined collection. Now, how do we actually write them down? How do we communicate what's inside our collection? Turns out there are two main ways to do this.
So on one hand, you've got what's called roster form. This is super straightforward. It's just the guest list, right? You list out every single member. But then on the other hand, you have the set builder form. And this is where things get really cool and honestly a lot more powerful. Instead of giving you the list, it gives you the rule for getting on the list. It's like getting the recipe instead of the finished cake. You can imagine how useful this is for gigantic sets where listing every single item would be just impossible.
All right, so we know what sets are, we know how to write them down. Now let's start sorting them out. Think of it like organizing a workshop. You don't just throw all your tools in one big pile, right? You have different types for different jobs. Same thing with sets.
First up is the one we run into all the time, the finite set. This one's pretty intuitive. If you can count everything in the set, and you know that count will eventually end, boom, it's a finite set. Simple as that, like the number of songs on an album or the number of chairs in a room.
And then you've got the flip side, the infinite set. This is where the counting just never stops. The set of all whole numbers is the classic example. You could literally count for the rest of your life and you'd never ever hit the last number. It just keeps going.
Then there's this little guy, the singleton set. It sounds kind of fancy, but really, it's just a set that has one and only one thing in it. For instance, the set of all people who are currently president of India. It's a collection for sure, but there's only one person in it. Okay, now this next one is a little bit of a brain twister. Can you have a collection of nothing? Like a totally empty box? Well, in set theory, the answer is a big yes. It's called the empty set, or the null set. Just think about the set of flying pigs. The rule is perfectly clear, but, well, nothing actually fits the description. That's the empty set.
All right, we've got our different types of sets all sorted out. Now comes the really cool part. This is where we start actually doing things with them. What happens when we smash them together, or find their common ground, or see what makes them different?
First up, we've got union. And the name says it all, really. You're just uniting two sets. You take everything from set A, everything from set B, and just smoosh them all together into one big new set. And if something is in both, that's fine. You just list it once. It's the all of the above option.
Then we have intersection. And if union is about bringing everything together, intersection is all about finding what's shared. It's not about everything from both. It's only about the elements that are in set A and also in set B. It's the overlap, that common ground.
And our last operation is called difference. The best way to think about this is literally subtraction. So if you see A minus B, it means start with everything in A and then just erase anything that also happens to be in B. What you have left is what's unique to A.
Okay, so union, intersection, difference, these ideas make sense, but they're still kind of words on a page, right? A little abstract. What if we could actually see them in action? Well, luckily for us, a logician named John Venn gave us the perfect tool.
And that's where this comes in, the Venn diagram. I'm sure you've seen these before. It's just an absolutely brilliant, simple way to make all of this stuff visual. You've got a circle for each set, and right away you can see how they relate to each other.
So let's see how this works. Remember union?
That was about combining everything. On a Venn diagram, the union is literally everything you see shaded here. The whole of circle A, the whole of circle B, and the bit in the middle. All of it. If it's in a circle, it's in the union.
Okay, now what about intersection? Remember, that was all about the overlap, what they have in common. Well, visually, it's exactly what you think it is. It's just this little sliver in the middle where the two circles cross over. That little piece is the only part that belongs to both sets at the same time.
And finally, let's look at difference, A minus B. You can see we're looking at circle A, but we've carved out that part that it shares with B. So what's left is everything that is only in A, and nowhere else. It's what makes A unique from B.
So think about where we've been. We started with these abstract rules and definitions, and we ended up with these super simple, intuitive circles that anyone can understand. That's the power of set theory. It gives us a language to make complicated relationships simple.
So start looking for this stuff. The friends you share with your partner, that's an intersection. The total number of songs from two of your favorite artists, that's a union. It's everywhere. Now that you have the language for it, what kind of hidden structures are you going to see all around you? Thanks for tuning in to The Explainer.